All right, wonderful students, here we go. Probability distributions. So let's get started. In a certain country, the probability that a baby that is born as a boy is 0.52, right? So 52%. That's basically the same relationship to help you understand. And the probability, there's a typo, that a baby that is born is a girl is 0.048. 0.48. A family has 2 children. If X is the number of girls born to a family, find the probability that the family has 0, 1, or 2 girls. Draw a tree diagram showing the possibilities for each outcome. Okay, this will help. And then create the binomial distribution table for P of X. Show all your work. All right, so a binomial distribution has a couple of factors. It needs to have a fixed number of trials. So in this case, it's 2 children, 2 trials. Next, it has to be independent and the probabilities can't change. So the probability that you have a boy on the first child is 52%, and then the probability that you have a boy as a second child changes to 51%. We can't do this. Something's changed, which would change the probability math. But it's not going to change. Each time, that's the overall experimental, empirical probability, right? Because the theoretical probability is 50-50. When you take a look at how genetics work, the baby making process happens, it's 50-50. However, yeah, that's pretty true. So that's why it's really close. It's really close to half boys, half girls. But just like we did with the flipping of the coin, in real life, the real experiment can change that probability slightly more, slightly less to one way or the other. But the more and more and more trials we experience, we'll see it gets very close to the theoretical probability. And that's the law of large numbers. But you can think about that later. Ooh. Okay, so let's go back to here real quick. 1 second. Boop, boop. Okay, great. I just wanted to close out of that. So let's just get started. So when they say draw a tree diagram, some of you guys have, it was very cute. So you drew an actual tree diagram, and I really loved that. That was great. Thanks for showing your personality there. Let's just go though. So the tree diagram is just like we used to do. So we'll start with the first beginning. So the first child, however you want to think of it, you just start with the first child. You could have a boy or you could have a girl. That's the first child, right? You can start like that. After you have your second child, right, it splits. You could have a boy. You could have a girl. You could have a boy. You could have a girl. That's basically it. We're done. The only difference is now we need to fill in the probabilities. And the way I was taught to do it was to write it on the line. So 0.52, 0.52. You can do it any way you want. You're just organizing the data. 0.48. Notice how 52 plus 48 is 100, right? Because that's how probabilities have to work. They have to be totaling up to 100% of the potential outcomes. All right, so far so good. So we can use this tree diagram to help us see where the math is coming from for a binomial probability distribution. So when we go to make our table, and now I'm just going to keep drawing it if that's okay with you guys. So sorry if it's messy. We'll switch to purple. So we have a table values. X is the random variable. X is representing girls, 0, 1, or 2. And this is, you could say P of X or just P. I don't really care. It's up to you guys. It just represents the probability that you get 0 baby girls, 1 baby girl, or 2 baby girls. Here we go. So the probability that you get no girls is only one path. You have a boy first, and then you have a boy second. So the math is exactly that. It's 0.52 times 0.52. So 0.52 squared. I hope that doesn't confuse anybody. I'm going to use my phone. Boop, boop. Calculator. 0.52 hundredths times 0.52 hundredths equals 0.2704. And if you remember, the reason we can do that is because those probabilities are independent. And when you have repeated independent events, you just multiply their probabilities to figure out the probability that those happen in that order, right? So like if you want to know the probability of flipping a heads, however many times you want to think that you'd get it in a row, you would just do 1/2 to the power of how many times you're flipping the coin. Think about it. All right, 52. So the next one is a little bit different. So we start still with a boy, but then we switch to the girl. So that math is different. We're going to get, let's go back to purple, 0.52, because there was a boy first, times 0.48. Cool. So we'll do that in a second. But I want to show you this. If you remember in the book, or if you remember in the examples, or if you watch the video, somehow we add for the single probability, the single outcome, or some of the other outcomes. And the reason is because we could have a girl first and a boy second. And then look at that. That's going to be 0.48 times 0.52. So 48% times 52%. But because it still means just one girl, the only difference is the girl is first or the girl is second. It doesn't matter. They're not asking for the order that the child is born, just how many girls are present. You can add these, or you can multiply one and multiply it by 2. Think about that. Because 2 times, here, you can check it. 2 times 0.52 times 0.48 equals 0.4992. All right, and you're welcome to do this math where you multiply this one, right? And multiply this one, and then add them together and check to see if you get 4,992 10,000ths. Okay, almost done. The probability that we get 2 girls, let's change to pink, is we get our girl first and we get our girl second. So it's going to be the 0.48 times the 0.48, or 0.48 squared. Think about it. Boop, 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 boop. Okay. That's a 3. All right, and now you can do a final check, because a couple of things about probability distributions that are big ideas is the total events, all of the probabilities that you're listing. For it to be a real probability distribution, it needs to add up to 1. You need to account for all possible outcomes. Otherwise, it's not a real probability distribution. You're missing something. And if it's close, right, when we're rounding decimals, it might be very, very close. It might be 1.01 or 90.99. But that's just because we are rounding. If we use the exact numbers, it would add up to 1 if you did it correctly. All right, so let's try it. 0.2704 plus 0.4992. 0.4992, I had a calculator error, plus 0.2304. Try it in your calculator. Ooh, that's not good. What did I do wrong? Okay, clear. 0.2704 plus 0.4992 plus 0.2304. 1. Okay. Calculator error. Happens to all of us. That's it. That's all. We're done with that one. Let's move on. Oh, so the probability that you get 2 girls is about 23%. Very similar to the boys, where you've got 2 boys, which is 0 girls, 27%. All right. Employees were asked how many times per week they exercise. The frequency table shows the results of the survey. All right, friends. So you can do this trick. Click this. Wait, hey. Control C to copy it. Come down here, Control V. And You can call this the relative frequency if you want. It's the same thing. But we're just going to need to change these numbers to a probability, a proportion, right? So we're going to need to use our calculator here. The first step when you're creating a probability distribution from a frequency table is to add up all of your trials or add up all of your employees. And so the frequency represents the number of employees who answered the above, those 0, 1, 2, 3, 4, 5, 6, 7, 8 times a week. So we're going to add 5, 10, 2, 9, 33, 12, 15, 3, and 1. So let's do that. 5 plus 10 plus 2 plus 9 plus 33 plus 12 plus 15 plus 3 plus 1, 90. Okay, I'm going to do it one more time just to make sure. 5 plus 10, because I'm using my phone calculator and it doesn't save my numbers. If you use Desmos, it will save all of your numbers and you can check to make sure. So I'm at 2 plus 9 plus 33 plus 12 plus 15 plus 3 plus 1, 90. Okay, so that's good enough for me to check it. Attention to precision is one of the big reasons we ask you to pursue mathematics. So go ahead and do that. And later on, you're going to need that type of belief to check your work because you're going to make mistakes. It's going to cause problems in your work, in your life, and it's okay to take that extra second and check your work. All right, so we've got 90 total. So then the math here is going to be 50 out of 90, 10 out of 90. Let's see, they want it as decimals. I would absolutely accept this. Absolutely. So just so you know. But we'll go ahead and write their decimal. Boop. What does that equal? Just because, 5 divided by 90, it's going to be messy. Yep, see, here we go. So now, depending on how we round to the nearest hundredth, see? Equals 0.11 equals 0.222. Yeah, okay. 1 divided by 90. No, 10. Oh, yeah. 0.022. 2, because it's 2. 2 divided by 90. Yep. Okay, perfect. 100th. Oh, just the 100th place. This should be 1/10. 0.1. Guess we could leave that just so you guys don't get confused. And the reason for that is 9/90ths will simplify to 1/10. This equals 33 divided by 90. 0.37. This equals 12 divided by 90. 0.13. This equals 15 divided by 90. Ooh, did I do the other one right? We'll see if I made 0.17. I'm going to check 1290 again. Yeah, it's still 3. All right. That should be 3/10. Hey, no, it's not. That should be 0. I'm going to make a guess. 0.03, just based on the pattern. I don't know if I'm right or not, but let's try it. 3 divided by 90. Aha, I was correct. 0.03. And then that should be 0.01. 0.01, but you can check it. 1 divided by 90. Yeah. Okay, so now let's just add those up, those decimals, just because I want to show you what happens when you round. So 6 hundredths plus 11 hundredths plus 0.02 plus 0.1 plus 0.37 37 hundredths plus 0.13 plus 0.17 plus, oh, it worked. 0.03 plus 0.01. Ha, it still added up perfectly to 1. So, well, that's good. That's very nice of them. So we have now our probability that we randomly ask an employee and they will say one of those frequencies that they exercise. So now we're going to go down here and answer this. You can show your work if you want. I'm going to talk about it. Less than 4 times a week. So that's that P parentheses X minus or less than 4. In the context of this situation, instead of writing this sentence out, what is the probability that we randomly select an employee from this company and they say that they work out less than 4 times a week? The probability that the random variable X is less than 4 is what that says mathematically, and then it's changed for every context. But that's one of the reasons we use notation, is we don't have to write out paragraphs and describe the story each time. We can share information, give each other data and numbers, and then we can all run the calculations and then refer back to what does it mean in the context of our data. So let's find out. The probability that an employee will work out less than 4 times a week, that's strictly less than 4 times a week, 3, 2, 1, and 0. So we add up all of those probabilities, and it looks like we get, here, 0.06 plus 0.11 plus 0.02 plus 0.12. That's going to equal 18, 19, 29, 0.29. You can check it, right? 17, 19, yeah, cool. All right, the probability that an employee works out exactly 6 times a week, well, just go look at it. Just go find it, 6. 15 out of 90 people work out 6 times a week in that group of employees. The probability that an employee works out 5 times or greater a week is going to be 5 plus 6 plus 7 plus 8. 0.13 plus 0.17 plus 0.03 plus 0.1. 13 plus 7 is 30. 34. 0.34. And there you have it. Those are the probabilities for the different situations. Companies like this because employees who work out, they are often healthier, which means they miss less days of work, which means they don't use the health insurance as often, so it saves them money, both with them being able to work more often and not utilizing the health insurance. So they're trying to promote health in the workplace. If you see that, you'll always see like, oh, a free gym or this or health, because they know that it's better all around, including for the human being. So hopefully that's why they're doing it, because it's better for us humans if we do exercise. But there's usually a financial incentive. Woohoo! All right, almost done, friends. And then, yeah, thank you for watching. Last year, the number of skateboards produced per day at a certain factory were normally distributed with a mean of 20,500 skateboards. That's wild. A day. It doesn't even make sense. The story problem is ridiculous. And a standard deviation of 55 skateboards. What that means is they've calculated how many skateboards they produce each day. On average, it's 20,500. One standard deviation is 55. So let's draw our curve. Oh, no, that's terrible. I ran out of space. Let's try that again. Okay, that's all right. A normal curve has the mean right at the center with 50% of the data to the left, 50% of the data to the right. So let's write our mean. We're not normalizing it. Notice we are not normalizing it. You don't have to normalize it unless you want to normalize it. Not yet. I'll show you why. You might need to normalize it. We'll find out in a second. Okay, so now let's do one standard deviation less, one standard deviation more. Well, the standard deviation is 55, so above it, if we go up, a standard deviation would be 20,555. Does that make sense? That's what a normal curve. This is why we like it, because we have that empirical rule, 20,445. Okay? Wow, so far, That's one question, two questions right there and right there. And we know some information using the empirical rule, the 68, 95, 99.7. That's one of the cool things about a normal distribution of data. Often machine productions follow a normal distribution, with the machine producing very close to the mean on a regular basis, but there's some variation and they account for that within the distribution. There are some days maybe they produce more. Maybe they got a 10-15 minute early start, the staff got there, started it going. Maybe they produced less. There was a malfunction and they had to shut it down for a few hours and then restart the system. So that's what happens with a normal distribution. On a normal day, they're producing the average amount. Different things will happen that will affect more production or less production. Hopefully that's helping you understand this normal distribution. It's wild how it works to me. It is. Anyway, okay, so that's one standard deviation below, one standard deviation above. So between those two green lines, that's where 68% of our data is. But remember, that means there's 34% here, approximately 34% here, and approximately 34% there. We're going to use the exact empirical rule. We're not going to use, if you use anything and you're close, it'll be correct. The big idea is just understanding how a normal distribution works, and then this nice pattern that people have discovered. Okay, so now let's read this next question. On what percent of the days last year did the factory produce 220,555 skateboards or fewer? Okay, wonderful. So what they're asking for here is the area under the curve to the left of 20,555. Well, that's good. We know that half of the data goes to here, 50% is on either side of the mean. That's the other cool thing. We know there's 50% over there and 50% over there. So then right here, since that's 50%, we just need to add that 34% and then say 84% of the days, wow, they produced 20,555 skateboards or lower. Okay. Let's go down to the bottom one. Why not? On what percent of days last year did the factory produce 20,445 skateboards or fewer? Alrighty, that's okay. That's just this one. Let's do green. That's down here. 20,445 skateboards or fewer. So now we want the area to the left of that green line. Again, that's all right. We can figure that out with the empirical rule. Look, we're not using tables. We're not using calculators. We just know how the normal distribution works. So we can make good estimations when we're talking to our employer, when we're thinking about our factory, when we are just trying to determine if we want to make a change. So let's see if this percent of days is acceptable. So remember, this is 50%, but we now just want this. So you can do 50 minus 34, or remember that that's 32%, or on both sides, total of 32%, and notice that this will then be 16% remaining. Excuse me. Okay, so only 16% of days did the factory produce 20,445 skateboards or fewer. All right, this guy, where's that number? First, before we bust out our z-score, which you totally can, you could totally use a z-score. You could use 20,610 minus 20,500 divided by the standard deviation. That is going to be 110 divided by 55. You can use a calculator, which tells me that I have a z-score of 2. What? A nice, neat number. Yep, it sure is. So let's go ahead and draw that. That's 2 standard deviations, 1, 2 above the mean. And that's where 20,610 will be. Perfect. We'll just move on to this next proportion. Alrighty. According to the empirical rule, let's bust out an orange, between here and we'll just kind of estimate it here. That's 1, 2. We don't know what that number is. Right now it doesn't really matter. 1, 2. Basically within 2 standard deviations on either side of the mean, we have 95% of our data. That's what that part means. So we have 95% of our data between those two portions. So that leaves us in the tails 2.5% over here and 2.5% over here. Because 95 plus 2.5 plus 2.5 is 100%, and the area under the curve is 1 or 100%. Okay? So that's the cool part. So now we're done, because now the question is asking us about this area. 20,610 skateboards or more. So they want this tiny tail above 2 standard deviations. They want to know what percent of days did our factory crush it. We were producing skateboards like crazy people. Only 2.5% of the days did they have an excellent overproduction of skateboards. That's it. I hope this helped you understand the normal distribution and probabilities in general, how they're useful, how they work. Keep thinking about the big ideas, because you're in this world. You've got to critically think. Don't give up. Even if it still doesn't make sense, I understand. Like I said, you keep going at things, you keep trying new things, and you just think about it. Eventually it'll make sense. You'll find somebody who can explain it better than me. You might find a interaction that starts to help you see how it works. Or you might go down a career where you're like, okay, I've got to learn it. So that must have to mentality forces your mind to focus and really try to put the pieces together. Or you might not, and you might say, this is good enough. I did it. I passed. I'm happy. I'm going to pursue something else. All of those options are okay. Just keep thinking. Never stop thinking. Okay? Thanks for watching.